In this lecture, we're going to look at the following 5 examples. So first, we will find an equation of the plane which is parallel to the coordinate yz plane and which contains the point 2, 4, 2. Then we will find an equation, it could actually be several equations, like in number 4, in this case it's actually going to be just one equation, that describes the set of points in xyz space which are equidistant from points P, 1, 2, 3 and Q, 1, 0, 1. So in number 2, I said that we're going to find an equation or equations. Again, in this one, it's actually just going to be one equation. But in number 3, it's going to be multiple equations, which we need to describe the circle in R3, which is parallel to the xz plane, centered at the point 2, 9, negative 4, and with radius 3. In number 4, we'll determine what set of points in xyz space is described by the pair of equations x equals negative 2 and y equals 4. Then we'll figure out if that set of points intersects the sphere given to us as x squared plus 2x plus y squared plus z squared minus 6z equals 90. Of course, we'll have to use completing the square to put that in standard form. And then we'll explain what we mean by perpendicular distance. So we'll find the perpendicular distance from the point 4, 1, negative 2 to the xy plane in R3. Then we'll find the distance from that point to the z-axis. Okay, so let's start with number 1. We want to find an equation of the plane which is parallel to the yz plane and which contains the point 2, 4, 2. To figure out what we need to do here, let's sketch R3. So here's the z-axis, the y-axis, the x-axis. So I'll label them accordingly. And then let's say this is the yz plane. That's one of our coordinate planes. Of course, I just drew this picture on a flat screen, so it's hard to see exactly what's going on. Let me label my picture. This yellow plane here is the yz plane. That's a good description of the plane, but it's not an algebraic description of the plane. If I want to give an equation of the yz plane, the equation for this is x equals 0. Now I would like to find an equation of the plane parallel to this one, but which passes through the point 2, 4, 2. So let me sketch that first, and then we'll figure out the equation. Okay, so here's that plane, and I've tried to move it closer to you if you're looking at this screen, because we know it contains the point 2, 4, 2. In other words, it passes through the value x equals 2. So it's hard to see on this picture, but we're imagining that this plane contains the point 2, 4, 2. Okay, so let's think about this plane now. What's true about every point on this plane? What could be a good algebraic description for this plane? Are there any constraints on our Cartesian coordinates x, y, and z? So are they free to be whatever they want? And notice we don't really have any constraints on y and on z. So just like in the yz plane, I could take y to be any value and I could take z to be any value. And we could find those coordinates on this plane so long as the x coordinate is 2. Okay, so since we're parallel to the yz plane, every single point on this plane must have an x coordinate of 2. And then once you have an x coordinate of 2, y could be anything, z could be anything. So the equation of this plane is simply x equals 2. All points in R3 which have x equal to 2 will land on this plane, and every point on this plane satisfies the property that its x coordinate is 2. So you satisfy this equation by being on this plane and vice versa. Okay, let's set up and solve example 2. So we want to find an equation that describes the set of points in R3 which are equidistant, or the same distance, from the points P1, 2, 3 and Q1, 0, 1. After we've written down the equation, I have a picture for you just so you can visualize what's happening. Okay, so what we want is an equation for the points x, y, z satisfying that the distance from xyz to the point P, so to the point 1, 2, 3, equals the distance from the same point xyz to the point Q, so to the point 1, 0, 1. So we'll say the square root of x minus 1 squared plus y minus 2 squared plus z minus 3 squared equals the distance formula applied to x, y, z and the point Q. So that's going to be the square root of x minus 1 squared plus y minus 0 squared plus z minus 1 squared. If these square roots are the same, then the radicands, or what we're taking the square root of, are also the same, so let's square both sides. And thus we have that the inside, so x minus 1 squared plus y minus 2 squared plus z minus 3 squared, must be equal to the inside on the right-hand side, so that's x minus 1 squared plus y squared plus z minus 1 squared. Conveniently here, the x minus 1 squareds cancel out, so let's just cancel those on both sides. Then I'm going to go ahead and expand all of our squared terms. So on the left, oops, I've left off a square here, let me drop that in. On the left, we're going to have y squared minus 4y plus 4 plus z squared minus 6z plus 9 equals y squared plus z squared minus 2z plus 1. Now all the squared terms cancel, so we have a y squared on the left and right, and also a z squared on the left and right. We can cancel those out. Now I'm going to put all of my y and z terms on the left and all of my constant terms on the right. So we get minus 4y, let's see, minus 6z plus 2z, so minus 4z equals 1 minus 13, so negative 12. And then divide out by negative 4, and we're left with y plus z equals 3. So that's the equation that we're looking for. That's the equation that describes all of the points in R3 which satisfy the property that their distances to P and Q are the same. Now, more and more as we work through the semester, you'll start to recognize what kind of object you're looking at. So what is this? Well, notice that it has no dependence on x. X is totally arbitrary. If I sketch y plus z equals 3 in the yz plane, let's see, I could write z equals negative y plus 3. So that's going to be a straight line like this. That's what this equation looks like just in the yz plane. Now, if we bring x into it and move this picture into R3, the x-axis would actually be pointing out of the screen straight at you, the positive side of the x-axis. So you would take this line and kind of move it towards you, and what you would sweep out in space is a plane. Let's take a look at this plane together with these points graphed in the program MATLAB. Okay, so here you can see R3 as shown in MATLAB, so you don't have the axes that I usually draw. Instead, they do this kind of rectangular cube. Here's the x-axis, here's the y-axis. You can see this is the origin in the xy plane, and then the z-axis, as we would normally draw it, would come straight out of here. Okay, so z is labeled over here on this vertical axis. Let's see, Q is the one that has a y-coordinate of 0, so this must be Q, and this point is P. And then this is the plane y plus z equals 3. Now if you're any point on this plane, then the length of this line segment would be the same as the length of this line segment. Again, this picture is at an angle, so it's not totally convincing, but those are the same. And that would be true of any point on this plane, and if you satisfy this property, then you land on the plane. So the equation we just wrote down, y plus z equals 3, describes any point x, y, z in R3 which makes this property true. Okay, now let's look at this example. We want to find the equations necessary to describe the circle in R3, which is parallel to the xz plane, centered at the point 2, 9, negative 4, and with a radius of 3. Again, let's start by sketching R3. So here's our z-axis, our y-axis, and our x-axis. Our circle is going to be parallel to the xz plane, which is this vertical on the left plane here. This plane, of course, is the set of points which satisfy the equation y equals 0. So that's the equation of the xz plane. We want a circle which is parallel to this plane, so it's going to kind of stand upright like this plane. Let me just try to sketch it, or at least sketch a circle which would be parallel to that plane, so something kind of like this. Again, it's hard to draw this in three-dimensional setting, but I'll just do the best I can. And then I put this down there because the z coordinate of the center is -4. So let's say this is the circle. So the center is the point 2, 9, -4, and its radius is 3. Now let's think about what has to be true about the Cartesian coordinates x, y, and z for every point on this circle. Well, if you think back to our first example, here we had two parallel planes. One was x equals 0, the other was shifted 2 units in the positive direction along the x-axis, so the equation of this plane was just x equals 2. We're going to have a similar fact here about the y-coordinate. So every point in this plane has a y-coordinate of 0. This circle being parallel to that plane means it's happening in the plane y equals 9. So I can imagine this circle as embedded in the plane y equals 9. Okay, so that's a description for the y-coordinate of every point on this circle. The y-coordinate has to be 9. Now, what is actually giving us the circular shape that we're looking at here? It's the behavior of the x and z coordinates. So our x and z coordinates are going to satisfy the equation of a circle of radius 3 with a center at 2, -4. I'm saying 2 and -4 because here we're just going to write down a circle living in the xz plane, and then we'll specify that that happens in the plane y equals 9. Okay, so the equations are, let me write the circular equation first. That's going to be x minus 2 squared plus z minus -4 squared, so z plus 4 squared, equals 3 squared, so equals 9. That gives us a circular shape for x and z. But we also need to specify that y equals 9. So we need both equations in order to describe this circle. One equation for x and z, and the other equation for y. Moving on to example 4 now. What set of points in R3 is described by the pair of equations x equals -2 and y equals 4? Does this set intersect the sphere x squared plus 2x plus y squared plus c squared minus 6 equals 90? I'll start in the usual way by sketching R3. So we have our 3 axes. X equals -2 and y equals 4, we don't have any constraint on z. So let me plot a few points that would make both of these equations simultaneously true. Let's see, for this, I'm going to need to go down the x-axis in the negative direction, so let me just include that part of the axis. Okay, so we'll come out to -2 on the x-axis and 4 on the y-axis. If I let z equals 0, but satisfied the equations x equals -2 and y equals 4, we would graph the point -2, 4, 0. Okay, I think that's the best I can do. So here's the point, -2, 4, 0. But z is not required to be 0 in this pair of equations. X is required to be -2 and y is required to be 4. So what we can do is lift this point up to stretch it in the positive z direction and drop it down to stretch it in the negative z direction. And what we'll end up with is a vertical line parallel to the z-axis, like this, where every single point on this line satisfies the fact that x equals -2 and y equals 4, with no constraint on z. Okay, let's answer the second question here. So does this set, in other words, does this line intersect the given sphere? Now what I could do is actually plug -2 in for the x variable in this equation, and I could plug 4 in for y. Because if I'm intersecting the line and the sphere, any points of intersection have to simultaneously satisfy this pair of equations in order to live on the line, and this equation in order to live on the sphere. Plugging in x equals -2 and y equals 4 is ultimately what we're going to do, but just for practice, let me go through and complete the square. That way we'll be able to identify the center of the sphere and also the radius. It's not required in this question, but it would be a nice thing to do. Okay, so I'm going to have x squared plus 2x plus 2 divided by 2, which is 1, squared, which is 1, plus y squared plus z squared minus 6z plus -6 divided by 2 is -3, squared is 9. And then we added 1 and 9 to the left-hand side, actually, so let me just go ahead and write 100. Okay, so that's 90 plus 1 plus 9. All right, the nice thing about completing the square is that it allows you to factor those terms where we added in new coefficients. So we're going to have that the x terms factor perfectly into x plus 1 squared. There was nothing to do for the y squared term, and then z minus 3 squared equals 10 squared, so equals 100. So just for practice, we can identify that the center of the sphere is -1, 0, 3. And the radius, which again we often denote by the Greek letter rho when we're working with spheres in R3, the radius is 10. Okay, so there's the center of the sphere. It happens in the xz plane. And then the radius is 10, so it definitely seems like the sphere is going to intersect our line. I don't think I can really realistically fit the sphere on the screen. And so it has a pretty large radius. Okay, so I extended the line just so that we could kind of see both points of intersection. Given that the radius is large, based on this sketch I made, which of course is not totally to scale, it looks to me like this line is going to intersect the sphere twice. Somewhere down here perhaps, and somewhere, say, up here. Okay, again, not drawn to scale, but just based on a sketch, this is the type of intersection that I'm expecting. Okay, if you're in the intersection of two objects, what that means is that you satisfy the conditions that each object requires. So to be in the intersection of this line and the sphere, both the equations describing the line and the sphere are simultaneously true. So I'll say the pair of equations, x equals -2, y equals 4, those kind of go together. That's a pair that describes the line. And x plus 1 squared plus y squared plus z minus 3 squared equals 100. Both of these must simultaneously be true. That could actually result in a difficult set of equations to solve, but here it's pretty easy because on the left we just have that the variables are constants. So if on the left both of these equations must be true, that means that x has to be -2 and y has to be 4. So let's go over to our sphere equation and plug in those values. So we'll have -2 plus 1 squared plus 4 squared plus z is really what we're looking for. Z minus 3 squared equals 100. Sorry to be running out of room here, but let me see if I can squeeze this on the last line. -2 plus 1 is -1, so squared is 1, plus 16 squared is 17. So we have z minus 3 squared equals 100 minus 17, so 83. Thus, I can solve for z now. I don't actually want to FOIL out that left-hand side. I'd like to leave it in squared form because I can take the square root of both sides and end up with z equals 3 plus or minus the square root of 83. Okay, so what that tells us is that this point on the top is the point -2, 4, 3 plus the square root of 83, because that's the higher value of z, that's the positive value. Whereas this point on the bottom, that's going to be the point -2, 4, 3 minus the square root of 83. You could wonder what other kinds of intersections between a line and a sphere could happen. So is it possible to have 0 points of intersection? Is it possible to have 1 point of intersection? Here we have an example of 2 points of intersection. Could you have 3 or more? And the answer is, well, if you imagine this line was way off to the right, then it's quite possible that the line and the sphere don't intersect at all. So you could have 0 points of intersection. How would you have spotted that with the equations? You might end up with something like z minus 3 squared equals a negative number, something that couldn't be true. So there would be no solution to trying to have both sets of equations simultaneously true. You could have exactly 1 point of intersection if the line is kind of lying tangent against the sphere. So try to determine on your own what it would look like to have a single point of intersection. And again, here you have 2. Could you have 3? No, you couldn't. So you couldn't have a line intersect twice and then kind of double back on itself, because then it wouldn't be a line. So you can have no points of intersection, 1 or 2, but you can't have 3 or more. Okay, last example in this lecture, let's find what's called the perpendicular distance, which you could actually just think of as the distance really, but here we're specifying what we're going to be looking for when we characterize how we measure distance in this example, from the point 4, 1, negative 2 to the xy plane. So that's going to be the distance from a point to a plane. Then we want to find the distance from the point to a line, in particular to the z-axis. Okay, so you can probably anticipate what I'm about to do. Let's sketch R3. So here's the x-axis, y-axis, and z-axis. Our point is 4, 1, negative 2. Okay, so this is the point. 4, 1, negative 2. So that happened 4 units down the x-axis, 1 unit down the y-axis, and negative 2 units down the z-axis. So this point in particular is sitting below the xy plane, down where z is negative. What do you want to call the distance from this point to the xy plane? Well, the distance is going to be, the shortest route that you could possibly take. So that would be like going straight up to the xy plane. The point on the xy plane which sits directly above the point P would be the point 4, 1, 0. So what is the distance from 4, 1, negative 2 to 4, 1, 0? It's not worth plugging into the distance equation because since 2 of the coordinates are same, the distance is how much they differ in the z coordinate. So that's going to be 2 units. Okay, so that's what we mean by perpendicular distance from, say, a point to the coordinate plane. Kind of imagine dropping it straight over to the coordinate plane in the shortest way that you can, which means zeroing out the relevant coordinate. So to get from this point to the xy plane, we would zero out the z coordinate. What would be the perpendicular distance to, say, the xz plane? To get to the xz plane, this kind of plane over here on the left, we would need to zero out the y-coordinate, which would involve traveling 1 unit from y equals 1 back down to y equals 0. So that distance would be 1. What about the distance to the yz plane? In that case, we would need to zero out the x-coordinate, so we'd have to travel from this point 4 units back to the yz plane, so the distance would be 4. And let me throw a new one in here. What about the plane z equals 5? What is the plane z equals 5? Well, x and y are unconstrained. Z has to be 5. So that would be a plane parallel to the xy plane, but sitting at an elevation of z equals 5. It's like taking the xy plane and lifting it up 5 units. So we would need to go from having a z-coordinate of negative 2 to a z-coordinate of 5. That would be distance 7. Okay, now let's look at the second part. We would like to find the distance from P to the z-axis. So let me clear out the work we've done so far to give ourselves more room. Okay, and also to make it a little clearer in the picture, let me extend the z-axis down by 2 units. Okay, now the distance from this point to the z-axis would be the shortest route we would take to get to the z-axis. So that would be like this route here. I'm going at an angle. So we need to zero out both x and y along this straight line segment from that point to the point 0, 0, negative 2. Okay, so the distance from P to the z-axis would be the distance from P, so from the point 4, 1, -2, to the point 0, 0, -2, which is going to be the square root of 4 minus 0 squared plus 1 minus 0 squared plus -2 minus 2 squared, so plus 2 squared. So we end up with the square root of 16 plus 1, or in other words, the square root of 17. So here I use the distance formula, but you could also fill in, say, sides of a right triangle here and treat this as the hypotenuse of a right triangle that lives in the plane z equals -2. It would give you the exact same calculation. Okay, so that finishes up these 5 examples. Thank you for your attention.